Hello everyone, this is Mingliang from Shandong University. My talk is titled Force-Directed Graph Layouts Revisited, a new force based on the T-distribution. This is our agenda. Graphs are everywhere and represented by different kinds of visualizations, and lots of efforts has been spent on finding good ways to visualize graphs. Among various graph layout methods, the force-directed placement (FDP) has gained the most attention in automating the layout of node link diagrams. The FDP method is designed as follows. All nodes are simulated using electronics, and there is electronic repulsive force between all nodes. And edges are simulated using springs, and the two nodes connected by an edge experience an attractive force from the spring. So this kind of method are also called the spring electric model. A typical problem of spring electric models are that each pair of neighboring connecting nodes is subjected to a large repulsive force, but spring attractive forces are small. Such situation would destroy graph structures by preventing connected nodes from being neighbors in the layout. Although recently proposed graph layout methods based on stochastic neighboring embedding, such as TSNet, allows to better preserve two-ring neighborhoods. They fail in efficiently maintain low stress areas and one-ring neighborhoods. In this paper, we revisit the spring electric model and propose a new short-range force based on the T-distribution and use it to compose the new FDP model, which can better maintain local graph structures while keeping the global structures of the graph. Now I'll briefly introduce some related works. We first summarized the related graph layout method. We divided this method into three categories. The first one is spring electric models. This kind of method applies spring attractive force on the edges and apply electrical repulsive force between all nodes. But this kind of method only works well on small graphs. The second kind of method is the stress model, in which a spring force with a fixed spring length is applied between the nodes. This kind of method is good at maintaining global structures, but fails to show the local structure. The third one is stochastic neighboring embedding, which is based on probability distribution and work better on capturing local structure, but the global structure is not that good. Most graph layout methods needed to use optimization solvers to create desirable drawings. For example, Barnhart approximation is the most commonly used acceleration method for spring electric model, which takes O(n) log n time complexity. Recently, a much faster method, random vertex sampling, has been proposed. It only has O(n) time complexity, but the layout quality is not that good. Here comes our approach. FDP methods follow two design principles. Nodes connected by edges should be close to each other, and nodes should avoid overlapping. Based on the above two principles, the force model of this method are limited to the category of power functions. This kind of methods face the following limitations. The extremely large short-range repulsive force pushes two nodes that should be closely connected apart. The small short-range attractive force does not prevent nodes within the cluster from being pulled out by a single distant node. So the spring electric model cannot guarantee that two connected nodes are always the closest neighbor. With this observation, we found that we need to add a new principle to preserve the neighbor structure. That is, nodes that have a connection between them should be closer to each other than nodes that do not have a connection. To satisfy the new design principles, we need to find a new force that meets the following requirements. Firstly, the force should have an upper bound for short distance between two nodes. Secondly, the force should smoothly reduce to zero as the distance decreases. And thirdly, when distance approaching 0, the magnitude of attractive force should equal to the distance. Fortunately, we have found a force function that meets all the above requirements, that is the t-distribution function. By taking the negative gradient of the generalized t-distribution function and simplify it, we get a force that exactly matches the three requirements, which we call it T-force. We replace the repulsive force in the classical force-directed model with the T-force and add a T-force as an additional short-range attractive force, becoming another component of the attractive force in the force-directed model. The final resultant force would perfectly meet the requirements and overcome the limitation of traditional force-directed models. To accelerate the computation of our model, we introduced an FFT-based algorithm, which is called IBFFT and was originally designed for accelerating t-SNE using fast computation of the following kernel summation, and the term complexity is close to O(n). Our method can be written in a similar form of the above kernel summation, so it can be accelerated by IBFFT and only takes O(n) time complexity. Now let's go to the evaluation part. To evaluate our method, we collected 50 graph datasets for test. 4 measures are used to compare the layout results. These measures are chosen to evaluate the graph structure preservation or graph readability. We first measure the efficiency of the CPU and GPU version of our IBFFT. For the layout quality, except the conversion to TFDP by random vertex sampling, that is obvious, we can see that the relative values of all metrics are very close to 0. For real results, TFDP by IBFFT using GPU produces almost the same results as the exact method and performs better than TFDP by RVS in global structure. For convergence rate, we also found that all methods show good convergence with increasing number of iterations, except TFDP by RVS. For runtime performance, we can say that TFDP by IBFFT using GPU is one order of magnitude faster than TFDP by IBFFT using CPU for large graphs, which is also one order of magnitude faster than the TFDP by Banhart. Overall, TFTP with IBFFT generates similar layouts as methods like TFTP by BH, while being much faster for large graphs. Next, we compare our method with different layout methods. For layout quality, our TFTP is the best or second best for the structural metrics like SE and neighborhood preservation, and also performs about average on the readability metrics. For real result, TFTP is able to present the overall structure of the data efficiently and is more accurate than other methods in maintaining the local structure. For runtime performance, the GPU version of the IBFFT based TFTP is 2 orders of magnitude faster than other methods on large graph, except PMDS, which is a linear method with bad layout quality. In conclusion, our TFTP model is able to generate high quality layouts for most graphs while being extremely fast to compute. Besides, our TFTP model can be further extended for better supporting the interaction exploration of graphs. For example, using a large repulsive T-force will distribute nearby nodes evenly, resulting in detailed local neighborhoods. On the other hand, a small repulsive T-force will move connected nodes closer together and reveal major structures. Also, for local exploration, we can enhance the attractive forces between the focal nodes and their neighbors for pulling them together, while using repulsive forces to highlight them. In conclusion, we revisit the spring electric model and show its drawback, and we propose a new short-range force based on the T-distribution and overcome drawbacks of existing FDP models. Lastly, we provide a fast implementation and demonstrate its effectiveness through a quantitative evaluation and extensions. More details can be found in our website. Thanks for your attention.